presenting parallel subgraph isomorphism of multi-core architectures, a comparison of 4 strategies based on research. We will start discussing the problem, then parallel approaches, the experimental results, and the conclusion. Subgraph isomorphism is the problem of finding a correspondence among pattern and target graphs. And in order to understand if the pattern is contained inside the target graph, how many times and where. And it has to preserve the structure of the pattern graph inside the target graph. And this means that we need to preserve the adjacency and non-adjacency among the nodes. This is also called induced subgraph isomorphism. This is an example of one of the solutions of these 2 graphs. And this is used in a different application, but it's an NP complete problem. And there are several effective sequential algorithms. The graphs are becoming larger and larger, so also the time required to find the solution is increasing in days or weeks. So it's time to work on parallel approaches. We started from VUF3Lite, that is a state-of-the-art algorithm that uses a state space representation where each state is a partial solution of this mapping function that we want to find. And in the example, we can see that first state is an empty matching, so we work iteratively by adding new nodes in this matching. And this search is the search of the solution is performed through a depth-first search with backtracking, and a set of rules are used to avoid exploring states that are not consistent with the constraint of the subgraph isomorphism. In this case, state S9 is a solution and is a goal state that is one of the states we want to search, we want to find. This kind of representation allows us to use a state-level parallelization. It means that each thread is responsible to explore a single state. We decided to use static thread pool that is started before starting the matching process. And global state stack is used to let the thread communicate each other, sharing the states. And we don't need to use backtracking. This is the first version that only uses a global state stack. And each thread explores a state and then put the descendant that are consistent with subgraph isomorphism inside the global state stack in order to let the other thread to get new states to explore. So each thread then takes states from the global state stack and explore these states by generating new consistent states and then put them in the global state stack, and so on. A new solution that we proposed is to add the local state stack, that is a private stack used by each thread together with the global state stack. So the global state stack is used to share the states among the threads. The local state stack is used by each thread to explore a subset of the state space without interacting with the other thread. This is because we need to find a trade-off. We need to find a trade-off among the use of the global state stack and the local state stack, because using only the global state stack can have a high overhead due to the communication when the number of threads increased. But using only the local state stack can be a problem because we can have an unbalanced workload if the thread works without sharing states with other threads. So it will explore a huge state space without communicating to the other thread and sharing the workload. First solution to balance the usage of these 2 stacks is to limit the size of the global state stack. So the thread will put new states in the global state stack when its private state stack is full. And takes new state from the global state stack when its local stack is empty. Then another possibility is to don't limit the depth of the local state stack, but limiting the descendants that are explored using the local state stack. In this case, we consider a root state, each state that is taken from the global state stack. And we count the number of descendants that we have inserted in the local state stack starting from the root state. When this limit is breached, we have to share the other states in the global state stack. So in this example, we can limit to three descendants. So when we arrive to 3, the additional descendants are put, in this case, S8 is put in the global state stack and is shared with the other thread. Another solution is to is still not limiting the local state stack, but check periodically if there are threads that are waiting for new states because they have finished their work. And in this case, we call it automatic work sharing, this strategy. And what is done is that after a period that is counted as number of states explored, a thread has to check if there are threads that are free of work, and then has to share a number of states from its local state stack to the global state stack that is equal to the number of threads that are actually not working. So some experimental results. We used NIVIA large and dense graphs dataset. In particular, we used 2 density 0.1 and 0.2, and we considered both unlabeled and labeled graphs. And we have measured speed up and efficiency to find the first solution and all the solution. In particular, what we can see from the results we get is that the solution using the local state stack achieve higher speed up, especially when the number of threads increase. So the speed up is quite linear with the number of threads in some cases. And as we can see also from the solution that has been achieved, that it's in most of the cases higher than the 60%. And then this is also for the first solution. Even if this is a simpler problem, we are able to speed up, considerably speed up the sequential algorithm, and also to achieve a very good efficiency, especially using with limited stack and with the descendant limited strategy. And also in case of the memory usage, this is the ratio between the memory usage of the sequential and the parallel algorithms. So this is a reference of how much memory we use. As we can see, in case of unlabeled graph, there is the higher increment, but this is due to the fact that in this case we generate much more states that are explored in parallel with respect to the sequential algorithm. In conclusions, using a state space representation allows to effectively exploit a fine-grained parallelism that in this case is a state-level parallelism. We have proposed 4 strategies to explore the state space in parallel. And as we expect, the use of a local state stack allowed to improve the efficiency of the algorithm. But of course, we need to go deeper with this analysis, and in order to analyze also on different kind of graph and data sets. Thanks for your attention.